All right, welcome to the next semester of the seminar. And today we're very happy to have Niall Smith from FU Berlin talking about the discrepancy of Hamilton cycles in random subgraphs.
Yeah, thanks for the introduction. Thanks, Jan, for inviting me. Thanks, Joseph, for setting it up. This talk is my master's thesis. So I've finished my master's in Berlin and got a PhD position in Dortmund. So that's where the story will continue. My supervisor is Olaf Parchik. So we're going to talk about discrepancy, which describes an imbalance. And rigorous studies start with study of Einstein equations with bio in number 2. And applications are all over, including product theory, computer science. And to warm up with a very simple example of what we will mean by discrepancy is for a graph on n vertices with a 2 coloring of the edges. If a Hamilton cycle has quarter of the edges red and 3/4 blue, then the discrepancy is a half. So it's the difference between the dominant and the less dominant stuff. So yeah, the great master Ehlers looked at a similar problem with a slightly different definition of discrepancy, but it comes essentially to the same thing. And 4 copies of a fixed family tree for maximum degree. So yeah, what I just said for our case, then the discrepancy of Hamilton cycle is the absolute value is the number of red edges minus the number of blue edges. So can you find a Hamilton cycle with high discrepancy here? Well, can you see the colors? Yeah. So yeah, so if you take there's the hourglass has a lot more red than blue. Or if you take the outside, so it's a lot more blue than red. But if you take the both sides, then you see where discrepancies that could be checked. So how about here? Can you find a Hamilton cycle with high discrepancy? Well, I'll spoil it, you can't. What's the reason? What's the reason? It's a Hamilton cycle. We have to visit every vertex, including this one. We have to go in and out. So we have to use at least 2 red edges. And all of the other edges are blue. So half and half, no discrepancy. So bearing that example in mind, can you find a Hamilton cycle with high discrepancy? No, because yeah, that's it. So now, yeah, Hamilton cycle got to visit all the vertices, including these 2. Got to go in and out. So 2 here, 2 here, it's 4, and then all the other edges are blue. So this is essentially the limiting construction, which gives. So later we're going to see 3/4 is a threshold where you can't improve anyone. It's the extreme value. So of course, we're looking at Hamilton cycles. So of course we start with Dirac and for the minimum degree, it's above half n, then the graph has a graph on n vertices has Hamilton cycle. So this is kind of where this is the result that started a lot of interest in discrepancy. Balogh and others showed that for arbitrarily small constant C and n sufficiently large, choose a graph of n vertices with minimum degree at least 3/4. Let's see C times n. Then G has a Hamilton cycle with very small discrepancy, but yeah, Cn over 32.
I'm sorry, I didn't understand. So we are heading for the largest possible discrepancy or the least possible discrepancy?
So we want to find the largest.
Okay, and then this is exactly, or it is at least this.
Yeah, at least.
At least.
Yeah, so it can be more. But you can, yeah. This result has since been improved. I think the constant has, yeah, so the 32 on the bottom has been improved, but our focus is that it can be bounded by linearly. Okay, so that's the deterministic side. We are looking at random graphs. So classic result for Hamilton cycle in a random graph for GNP. Then Komnenos and Csaba already showed that this is the threshold. For a random graph having Hamilton cycle type probability. Then more recently, for an arbitrary host graph with high degree, so the minimum degree of the host graph is the Dirac threshold n/2. Then if p is above a big constant times log n/n, then high probability delta Hamilton cycle. Just point it out now. Yeah, so this is obviously bigger than this. Come back to that. And then later on, Gishboliner, Krivelevich and Michaeli showed that for. So now we've got P it's as small as it can be. It's the it's the Hamilton cycle threshold of Komnenos and Csaba for P greater than this. Then every random graph GNP is asymptotically almost Jury such that any arc covering of the edges gives Hamilton cycles with at least this many edges the same color. Not exactly in the language of discrepancy, but first you can translate it very easily. For r equals 2, then if r is 2, then you've got essentially 2/3 of the edges same color, and then discrepancy is there. So this is what I've just said so far. Hamilton cycle with linear discrepancy deterministically in every graph. For GNP, it could be P above the Hamiltonicity threshold, and then Hamilton cycle exists for minimum degree this, and for a random subgraph, as long as the host graph is a Dirac graph and P is above T times log n/n. So what we asked is, what Olaf asked, is that can we combine the results and see can we find a Hamilton cycle with linear discrepancy asymptotically uncertainty in a random subgraph for big constant P above C log n/n, G with minimum degree 3/4 plus C times n for small c. So what we've done is we've taken you can see, right? So the threshold probability that we're asking for is from here. The host graph minimum degree is from Balogh, and the methods that we're going to try and use to show it are from this result here. So the result that we got was that yes, possible you can combine them for arbitrary arbitrarily small constant, there's another constant such that for big C, for graph on n vertices with minimum degree at least 3/4 plus c times n random subgraph GP of that graph with high degree with p above the threshold c log n over n satisfies that any two coloring with edges has a Hamilton cycle with discrepancy at least k. Any questions so far?
So here by the random subgraph, you mean like with probability p, you take the vertex and then you take a new subgraph, or what?
So around when I say a random subgraph, I mean you have this host graph with high minimum degree, and then each edge you take with probability.
Okay.
Yeah. So just when we were about to submit, then we found out that some other people got there first. Jing, and Leon. So I can't claim these for myself, but they did an excellent job and recommend their paper. So how did we do it? You sample a random graph, take an arbitrary coloring of the edges, red and blue, and then you apply a version of the regularity lemma. You obtain a partition with t parts, reduce graph H, and minimum degree 3/4 plus t over 2 times t. So if you want to talk about the normalized minimum degree, so the n is now t per square in the reduced graph, and we've lost a little bit in the constant, but it's essentially the same. So we can define from the original graph to the regular partition. You can define the coloring. You just take, so an edge in the reduced graph refers to sparsely epsilon regular pair. So two parts of the graph with lots of edges between them, and then you just take the color which appears more often. So I'll have some pictures in a minute to make it a bit more clear, but just to give an overview, press on for now. Take a Hamilton cycle in the reduced graph using the result of Balogh and this induced coloring. And a Hamilton cycle, of course, is two perfect matchings. So I mean, there's some, if it doesn't have an even number of parts in the partition, you just put one more, and you take the matching with a higher discrepancy. For each edge in the matching, then in the reduced graph, then you go back to the original graph, and then you can find a long path. And then you join the long paths together using the other matching of the Hamilton cycle. And then finally, you can extend. So what you get is a long cycle on most of the graph, and then you can extend this using the expansion properties of the random graph. So what we did that was new is basically step 2. And the other things we did the same as, so we lifted them essentially from a paper of Krivelevich, Michaeli, and Gishboliner, which was kind of the paper that provoked the question of his thesis. And there was a little bit of work to extend the long cycle, but essentially it was the same as the paper of Sudakov and Krivelevich about Hamilton cycles in random subgraph. So very briefly about, don't know if everyone's heard of sparse regularity, but you probably heard of classic, the normal regularity lemma. The only thing that changes here is that, so the definition looks the same, so you've got this Q here. The idea being that So stop me if this is like too easy, but yeah. So with fast graphs, as the edge density gets less and less, and eventually every pair of sets of vertices is epsilon regular. So you introduce this this control. So the sparser it becomes, then the stricter you get with the regularity definition. And then if you set this Q to the density of the graph, then you get this definition sparsely regular, which you denote with these brackets. And then with this different definition, you just get the same, you can have the same statement as the Sudakov regularity lemma. And it was a lot of work to prove it, but Alex Scott did it in 2011. So this is essentially the same as the lemma, only you've got these. Just the same as Samarelli's original result, only you've got these extra brackets here. So okay, and then so this is something that we came up with to describe the relationship between a host graph and the random subgraph. So what we're saying is that for every two sets of vertices where the edge density isn't too small, then you get the same. It's the same proportion of edges. So yeah, it's the same proportion of edges in the random graph compared to the host graph, and it's a random subgraph of a host graph, but the proportion of edges is roughly evenly distributed all over. So we use, why do we do this? With these properties, then you can show what we did, and why is it useful? Because if you've got a random graph, then with high probability, then it does this. So we can stop talking about random graphs, start talking about these relatively pseudo random graphs. So this is then this is the key lemma that pushed through our results. It's a degree version of the sparse regularity lemma for these epsilon delta p relatively pseudo random subgraphs. Okay, so I think this is where the pictures start. So you might recognize this, or you might recognize this from the Samarelli regularity lemma. What it says is that every graph, every sufficiently large graph, can be split into a bounded structure, so that these are clusters, so these are sets of vertices. Then between these parts, the edges are random-like. And the sparse regularity lemma, which I just showed, says essentially the same thing for sparse graphs. So there's I've colored these edges so that the lighter they are, the fewer edges are between them, and you can introduce a cutoff density so that by taking out the low density pairs, you can show that the produced graph, so this thing here, has roughly the same degree as, so that the same normalized degree as the original graph. Now, if we've done it on a graph that's colored, then so I've made these various shades of purple to show that. So yeah, for example, this one is supposed to be, these two are supposed to be very red. These ones are supposed to be more blue. So if you do a sparse regular partition of both of the red graph and the blue graph at once, then you can show that you can get a partition that's sparsely regular in both colors. And then you just color you color the reduced graph by taking in each edge. So, for example, this edge here is already mostly red, so stays red. And this one's mostly blue, so it stays blue. This one's kind of in the middle, it's purple, so you just take one of them. And then what we're saying here is that we've got a reduced graph with a coloring where we know that each edge, if it has a color, then first of all, it's guaranteed to have a minimum density. And second of all, we know that in between these two parts, when we go back to the original graph, there's a lot of edges of that color. So this is where we apply the deterministic result of Balogh. So yeah, our graph is going to be very big. It's going to have a lot more than 5 parts. You apply the Balogh's result, you get a discrepancy result on the reduced graph, fit it into 2 perfect matchings, which you'll see on the next slide. So if this is the Hamilton cycle we've got from Balogh, then here's one matching, here's another. We take the one with the higher discrepancy. Then, so each edge in this matching, like for each edge to be matching, then we go back to the original graph, and we take a result of that. Yeah, that's widely used by Krivelevich to find. He's got this. Yeah. Krivelevich has done a lot of work on long paths and Hamilton cycles and random graphs, and he's got this trick using the properties of depth first search that is very effective. If you have two subsets of the vertices, and you know that between any subsets of those of a certain size, then there's always an edge, then you can show that G has a long path. So you do that in the first matching. Yeah, you do this in the first matching, and then in the second matching, you just take any edges which are close to the ends, and then it gives you this long cycle. So where are we now? Yeah, so this is just saying what I've just said. Yeah, so this is where we are now. So the big circle is the whole graph, and we found a big cycle on most of it. And the problem is we've got some vertices left over. So what do we do with that? So what Michaeli, Krivelevich, and Gishboliner do is they prepare that graph. So they set some vertices aside at the beginning, and that's what we're going to do as well. So we set some vertices aside at the beginning, which have a high connectivity to the rest of the graph. And we do all the other steps again on the remainder of the graph. And then we can show that no matter where the leftover vertices come from, you can always find a long path which covers all of these vertices and whatever we set aside, and then you can insert that into the Hamilton cycle, into the long cycle and get a Hamilton cycle. So, yeah. Are there any questions now? Okay. So these are kind of the technical details of how to finish off the long cycle into a Hamilton cycle. Yeah. What we're saying is that we can make a partition where eta is the number of vertices we satisfies, so that for every long cycle in the V diamond, which is long enough, then we can extend it to a Hamilton cycle. And the tools we use are essentially Posar's rotation extension technique. However, we lifted the techniques from the paper of Krivelevich and Sudakov, and we were able to put it through as it was. So the way it works is by having one subgraph, like one graph that does rotations and the other one that does extensions, and instead of looking every time, but doing it step by step, then you can show that graphs that fulfill certain properties with high probability will do this for you. So you can package everything in these one graph that had parameterized with theta. Yeah, and then basically it goes through. What I wanted to say a few more words on is the proof sketch of the RT lemma. So so epsilon is the parameter that is the target parameter. So what we're looking for is a sparsely epsilon regular partition which has minimum degree in the reduced graph. So we take a much smaller epsilon and take epsilon prime regular partition of GP. And each part that participates in at least square root epsilon prime T primes regular pairs, moves to the exception set. Rename the parts and delete all the epsilon remaining parts to the large and exceptional set, the regular pairs with density less than dq, or that are contained in one part. So now take an arbitrary non-exceptional part vi and count the outgoing edges. As you can denote the size of vi by m, and write, so that's the notation for how many edges are leaving vi and t prime. So there must be at least this many, right? Essentially counting half edges. This is what we get from the relatively pseudo-randomness. There can be at most this many edges going to the exceptional part, this many going to irregular pairs, and this much going with low density, and this much inside one part. So we get this very long sum, which is repeated here. But yeah, collect the terms, and then on the other hand, because of pseudo-randomness or the relatively pseudo-randomness of the subgraph, then each other part can accept this many half edges from this vi. So the number of sparsely epsilon regular pairs with density greater than dq that vi can participate in is at least so. We collected, we put the sum on the top and what another part can accept on the bottom. And yeah, so all of the constants end up in here, and what the p's cancel. So the difficulty was transferring from a classic result to the sparse result. So the p's cancel, you get m's canceling here, and then the m. So the total number of vertices divided by the size of a part is essentially the number of parts, and the delta and gamma are the parameters of the pseudo randomness. Means that because these are you can choose these to be as small as you want. You can essentially get C to be you can get as close to the original C as you wanted. Yeah, so that's kind of a bit of machining. So yeah, that was my talk. Thanks for listening, and thanks again for listening.
Question.
Yeah,
Yeah.
I haven't got these pictures saying that the happens. Did they use a similar technique as us?
So their result was even stronger because they showed that you can cut out a host graph and then take the subgraph after you've done it. But I mean, it's in some ways it's similar, but I wouldn't.
I have a nerdy question. So first I was surprised you are using the Alex sparse regularity, but then you said, right, but anyways, we have this relative pseudo-randomness. Can you just use this, would this relative pseudo-randomness allow you to use this Kohyakova variable?
Exactly. We didn't need to use one. Yeah.
But it would go through as well. I mean, I'm not saying that you should, I'm just saying.
Yeah, I mean, we basically used Kohyakova. Yeah. Yeah.
Mm.
Yeah, Kohyakova was the second exam.
Okay.
Yeah. I mean, I only asked him to do it after. Yeah.
I see. Okay. And then obvious kind of stupid question, more colors.
Yeah. In fact, yeah. So yeah, it's very easy to generalize to more colors.
Mm-hmm.
In fact, the conference where we met, I also met Andrea Freschi. He was part of the team that generalized the class results. So, and then you can just do the same thing, and it goes through. And yeah, behave technicals and beyond, they also do it for all more kind of.
Mm-hmm. Mm-hmm.
Question? Okay, so maybe is that something related not with Hamilton cycle, but maybe let's say that mentioned with some other stuff.
Yeah, so all of the results for Hamilton cycles, I mean, yeah, obviously you can improve them to or apply them to perfect matching, and then you just get the same thing with the constants half. And that's from the papers I read, then that's also as good as it gets.
Spanning trees?
Spanning, yeah. So I haven't thought about. I mean, I haven't looked at spanning trees, but you could do it.
I know it's not what the talk was about, but you happen to know, you mentioned at the beginning some applications in number theory.
Yeah. So I'm not a number theorist, but so my understanding is that so Dirac equations are roots of polynomials with integer coefficients, and then the buyer, the guy who started looking, he was interested in characterizing rational numbers according to, characterizing irrational numbers according to I've forgotten what it's called, but it's essentially the decimal expansion. If there's some remainder that occurs more often than others. So, I mean, this is my very, very bad understanding, but if you write an irrational number out like forever, then you look, how often does 3 come up? How often does 7 come up? Is it evenly distributed or not? And his results, again, really like badly stated, but his result is that a true irrational number has no discrepancy. So all of the numbers come up all the time. Yeah.
Thanks.
Yeah, thank you.
Are there any more questions? If not, we will thank the speaker again.